So if you don't know me, I'm Rohan. I'm a fifth year student working with Alex and Fred Kilstead. I also work at NVIDIA Research with Mike and Michael Garland. So I'll be talking about Legate Sparse. So this is work done by a lot of people. Kind of people most involved right now are me, Sriram, and Wanshan. And then this is building on a ton of work by the whole Legate team at NVIDIA. So there's a ton of people that I'm not going to mention directly. Um, Okay, so Legate Sparse on one slide. Some of this has been said by Wanchen, but I'm gonna kind of just go over a bunch of this stuff again because I think it's pretty important. So Legate Sparse is a system that is going to automatically scale your SciPy sparse programs across clusters of any size that you want. So it's another step in this goal of the whole Legate project to make HPC more accessible to people, especially those people who don't know how to program supercomputers. So to show this off, well, here's this Python code on the side. It is purely NumPy and SciPy code, except on the top, we've replaced the SciPy sparse import with Legate sparse, and we've replaced the NumPy import with CuPy numeric. And then the rest of the code is just the normal Python that you would have written. So we create a sparse matrix. We're going to do some work to make it PSD, and then we're going to do a conjugate gradient solve. And you'll note that there's the interesting parts about this code is that there's sort of data flowing back and forth between the dense components running on CuPy numeric and the sparse components running with Legate sparse. We're sort of passing this distributed data back and forth easily. And we have this separation of concerns where the sparse library is doing all the sparse stuff and the dense library is doing all the dense stuff. And that's kind of how we want our libraries to actually work. And then you can actually get great performance with this code. So I have a scaling plot on Summit, somewhat old plot. But you can see we're comparing against SciPy. We get a big performance boost over SciPy, which is actually using all the cores available on our machine. And we can be pretty competitive with PETSI. And if we actually want to go to the GPUs, we can be competitive with PETSI on GPUs as well and CuPy in a single node. And then scale out to kind of how as far as we want to go. Whether we want to solve a problem on just a single GPU or we want to solve a problem on 192 GPUs. So the bigger picture, Wanshan showed this before, but Legate Sparse is just one library inside this whole Legate ecosystem, and the ecosystem is growing. We have a lot of separate libraries like CuPy numeric for doing dense array computations, Legate Sparse for using sparse stuff, data frame for data frame operations, and then data analytics and machine learning libraries. And so the whole point is that these libraries are all kind of separate. They use pieces from each other. So dense components from CuPy numeric are used in all these other libraries. Sparse stuff from Legate Sparse can be pulled into these other libraries. And it all is actually running because of the whole Legate runtime system, which of course is living on top of Legion and RHEL. So as with many other talks, I wanted to give a bit of a retrospective on where the project has been since the last region retreat 2 years ago. And so back then, so here's a slide from that talk I gave in 2022. So back then, Legate Sparse was an in-progress NV Research internship project. So it was kind of one of the first Legate libraries that has actually been built on the new Legate core. And back then, we were, I was just hacking on it, trying to get some initial results. And so we had to do a bunch of stuff to change the Legate core at that time to actually get the features we wanted. And we also had to change QNumeric to kind of do what we want. So if you wanted to install a library at that time, you had to install a custom version of the core, a custom version of QNumeric, and it was all a nightmare. And we had a couple small results, okay performance, kind of scaling up to some small scales on small problems. So today we've actually grown a lot. And the first thing is that it's a real thing. So this is actually an official NVIDIA a product alongside of QNumeric. It's a much more an alpha version than QNumeric, and a lot of the work has been done by Sriram. I don't know, he's not here, he might be on the Zoom, but Sriram has done a lot of work in actually adjusting all that code, making sure it's closer to production ready than before. And then the cool part is that it's actually all the stuff we needed to do for the research has now made it into the real QNumeric and Legate core. So you can just install Legate, and I'll show the command later, but you can just install Legate Sparse with the same versions of Legate and QNumeric that are deployed right now. We wrote a paper about it, and so part of writing the paper, we built a bunch of non-trivial applications with it that I'll talk a bit about later. But if you go read the paper, it's actually secretly a paper about the Legate core, not really about building the sparse library. And we also picked up some interesting users that like real people actually want to use the software. So I'll talk about this and some results next, but there are actually people who want to use this software, so it's pretty cool. So one such user is this company called NPCI, National Payments Corporation of India. They run a lot of transactions in India go through this industry. And they basically want to try and detect fraud in the data, in the transaction data they have. So they have these big sparse matrices where on the rows and columns of that matrix are individual people, and then there's entries in these matrices when person A sent some data to person B. And they're trying to detect fraud through some various ways in this data. And basically what they want to do is they have these gigantic sparse matrices that they want to run SP-gems on. And each self-multiplication of the sparse matrix is kind of extending the paths in these graphs by doubling whatever the path was before. And so, of course, they're going to get humongous speedups over CPU clusters, which is what they're using before. I think they're reporting like 50x. Just, of course, if you use GPUs, a cluster of GPUs, you're going to go much faster than a couple CPUs. But I think separately from actually the performance speedups, the reason why they liked this software was more of how easy it was to use, and because you're able to actually combine it with cuNumeric, or sorry, cuPyNumeric. Like the dev techs who are involved, they could just kind of write their NumPy code that loads their data from disk and then pass it to the sparse matrix and then not worry about any of the distribution of all the complex sparse data structures. It just kind of worked. And I think that's a testament to, that's like another angle. Jeremy was talking about that productivity performance curve. Like if you really just want to get something really fast, like Legate, you can do that really easily with this stuff we built. In terms of other like more scientific computations, I think last was really more of a data analytics kind of thing. We've written some pretty interesting scientific codes. One such code is a geometric multigrid solver. These are pretty tricky to write in MPI. Kind of you have to deal with scaling this grid down and only parts of your cluster you want to do the computations on. And that's all really easy in Legate. You kind of just write a bunch of SPMVs and you can annotate a little bit what subsets of the cluster you want to run on. And so similar results before, we've shown good speedups over SciPy, competitive with cuPy. Originally, we had some pretty great scaling with CPUs, but the GPUs fell off a bit. Mike fixed this with some of his equivalent set refinement heuristics, and so we're able to get actually pretty perfect scaling out of this multi-grid solver from pure Python. And then another interesting piece of code we wrote was this simulation of Rydberg atom arrays, some quantum phenomenon. And the core component of this was like a Runge-Kutta solve. And there's a similar story of, you get a big speed up over SciPy, then you get even more speed up when you get a GPUs. And so with not that many code changes, you can just start solving problems way bigger than what you could before. So while the performance falls off here, I'll note that the application itself has some all-to-all behavior. So as soon as you kind of have to start going over the network, your network gets saturated and your performance isn't as great. I think the interesting part of this code, it's similar to what Wanshan was talking about before with Rory's experience in Legate Boost, but this particular code used the SciPy integrate method. And so that code, if you go look at it, I forget the exact year, but it was written back in like 2000 or 2005 or something. And so it's some old Python code that was purely sequential, and no one was, like Legion didn't even exist at that point in time, right? So there's no way they could have known. But with the Legate framework and all the work we've done, you can just take that code, make a few modifications here and there to avoid blocking and make sure that you use functions we have. You can run that at scale, and you can solve like, I don't know, problems order of magnitude faster than you could before. So it's kind of a testament to what Legate can do for you. So that was kind of the end of the victory lap, I guess. So I wanted to spend a bit of time talking about how the library itself works. And part of that is going to be talking about how the abstractions that are available inside of Legate make it easier to develop these kind of libraries, and how those abstractions actually get this feature of composability where you have independent code working together and achieving pretty high performance. So I was surprised that we didn't have this picture yet before, but we have this in a lot of slides. So the way that Legate works, right, is that you have a bunch of these different components in your library. These individual operations like calling matrix dot, matrix multiplication from different libraries, and they all are going to issue tasks into the Legate runtime system. And then Legate, gives a separately computed dependence graph, find out which of these computations from different libraries depend on each other, and then actually execute them on the machine. And this organization of the library, of course, has many benefits where you can find opportunities for parallelism across library boundaries that are difficult to express normally. And then I think the really interesting part that I will I'll reiterate many times in this talk is how it enables the individual components of your library to be logically isolated when you're building it. So when you're writing the SPMV, you don't care about what the sort or the SPMM is doing. You just write what your SPMV is doing. And the framework is plugging that into the remaining components of the program. So like sort of this picture I showed you before is about uh, composability in terms of correctness. Like how did you make sure that tasks that depend on other tasks don't run before they should and stuff like that. But then the real important part about composability, or one aspect of it, is making sure that you can share your distributed data in the right way. So Wanchan talked about earlier these partitioning constraints. I'm going to talk about them more and show you a little bit of different code, kind of the lower level API of using them. And partitioning constraints are a way to allow you to share, or these libraries to share distributed data without introducing unnecessary communication at boundaries of these libraries. So if you think about a standard Legion program, and the same thing applies to MPI, when you write a Legion program, you're usually saying that I want to do this index task launch over this partition. So you have embedded the partition you want to use in your program. And if you try and build libraries that way, what's going to happen probably is your first library is going to say, hey, I want to use this row-based partition of some tensor or some region. And that seems like a perfectly reasonable thing to do from the view of the library of just like inside that library. And then perhaps a second library you want to use says, hey, I want to use a tile-based partition of the matrix. But there's no real reason I had to do that, but I had to sort of pick one when writing the library. And then now if you know that second library could have actually used this first partitioning, well, you can induce a ton of extra communication at the boundary of this library to just shuffle data around unnecessarily. So partitioning constraints basically delay the choices of what partitioning you want to do until the runtime where you can actually see all the computations that you're executing. So then perhaps you could have made a different decision. Like maybe later you could have said, hey, the second function should actually reuse that first partitioning to avoid the data movement. And then these constraints are the ways that the applications expose to the runtime which of these different partitions you want to choose. So a simple example, Wanchan gave one about FFTs later, but I'll show you a smaller one that will help the discussion for how a sparse, launching tasks over some sparse data might work. So if you want to implement an element-wise addition, what you might do is, you're going to create a task launcher that's attached to some C++ code or CUDA code that actually does the add. And then, you're going to add your regions. You're going to say, I want to write to C. I want to read from A and B. And then, normal Legion, you would say that here's the exact partition of A, B, and C I want to use. But with these constraints, instead, you're going to say that I don't care how A, B, and C are partitioned, but all I care about is A, B, and C are partitioned in the same way. And so for an element-wise addition, that makes complete sense because I don't care what exact orientation the particular subregions are in, as long as I can access the same element of A, B, and C. So in this case, you could pick tile-based partitions if someone used them in the past, or row-based partitions if someone used them in the past, or like there's a previous example of if you load some data from disk and it's partitioned in a weird way, if you're doing then a bunch of element-wise operations that you can just keep the data as is, way you load in a disk. And the nice part is that the task body itself doesn't care. And so this is like very close to real code. Okay, so to see how this works for some sparse computations, there's two such constraints that I'm going to use in an example. So we saw the alignment, which just says equal partitions. Another such is this image operation, which is exactly the dependent partitioning framework inside of Legion. And so just a quick reminder about images, if you haven't seen them before. Images basically are talking about how do you relate partitions where one region has pointers into another region. So an image, so there's two kinds of images, by just like a direct image or by range. And so the direct image is when this source region contains coordinates in the second region. So an image is just saying that however the source is partitioned, I want all the pointers in the destination to be in the same corresponding partition. So in the top one, so say this green region, this green partition, has coordinates 1 and 3 in it. So the image constraint just says the resulting partition in the destination, those coordinates 1 and 3 must also be in the green partition. And then the range is kind of the same thing, but instead of individual coordinates, you have these like little ranges. So you can express like this coordinate 0 to 2, if that's colored red, well, then the corresponding range 0 to 2 in the destination should also be in the red partition. So these are ways to talk about sort of data-dependent relationships between regions. All right, I didn't say this earlier, but if you have a question, just interrupt. Same with the other talks. So we're going to use these when we actually talk about how Legate Sparse represents its sparse data structures. And so the nice thing about Legate is the way that these flexible partitioning constructs you have, you can actually just directly take your serial like CPU implementation of a CSR matrix and just turn everything into regions, and it turns into a distributed representation. So the way that, if you haven't seen a CSR matrix before, the way that it works is you have basically a dense encoding of the rows and a compressed encoding of the columns, meaning that for each of the rows, you have some metadata that says how many non-zeros and like where in this next array are those non-zeros stored. And then inside the CRD and vals arrays, you basically have the non-zero coordinates themselves, as well as the values at each non-zero position. So if we look at the first row, so we're going to see the data in the first row, we look at the pos array at index 1. And then we see, OK, we've got the coordinates, the positions 3 and 4 in the CRD array is going to encode the non-zero values in that row. So if we go to position 3, that's non-zero coordinate 1 corresponding to D. And then position 4 is this non-zero coordinate 3 at value E. So to talk about how Legate Sparse is going to launch computations over this, we can just write a little SPMV that will, I think, kind of develop basically what most of the implementation looks like, and then what kind of Legate is doing for you under the hood. So if we want to write an SPMV, okay, we're going to, our output mech vector is Y, and we're going to read from this input vector X. So, we're going to do some computation legions. So we create a task launcher. We're going to write to this value vector Y. And then we need to read from all of these matrices, these vectors that make up A, and the actual like dense vector X. So the first thing to do is, so we need to tell Legate how we want to partition this using constraints. So the first constraint that I'm going to add is an alignment constraint between the output vector Y and the pos array of A. And the way that this makes sense is that, okay, well, each output of Y, each element of Y is the contraction of the corresponding row of A times the vector X. So the pos array is encoding the metadata needed for a particular row of A. So for each coordinate of Y I want to compute, I need that same coordinate of A to look at. The next constraints we're going to add are images between the pos array and the CRD and values arrays. And so this kind of makes sense because that pos holds ranges of CRD and vals that are needed to actually look at the whole metadata of A. So that image is kind of directly what you saw before. And the final piece is another image from the CRD array into X. This one's a bit trickier, but the way to think about this is that the way I'm gonna do that contraction between a row of A and X is I'm gonna look at all the non-zero coordinates of A, and I'm going to like look up those corresponding values in X. And so the image kind of directly expresses that and gives you these kind of halo-like or some very sparse partitions of just the data of X that you need. And this is actually like the entirety of the task launching code for SPMV. So we're going to go call kusparse on the inside, but you can see that there's a lot of stuff that like dynamic analysis inside of Legate and Legion that are going to figure out the exact pieces of X and A of CRD and vals that we need. But the nice thing about this code is with constraints, it is going to adapt to however the matrix A is already laid out. So if you load A in some row balanced non-zero form, then we can just reuse that partition exactly without ever having this implementation know about that fact. So it's very nice. Okay, so to implement most of Legate Sparse, what it did back when it was research to actually fill out a lot of the library was to leverage this prior work we did called Distal that Alex mentioned. Basically, inside of Legate Sparse, there's a ton of different sparse matrix formats. There's a ton of different operations we need to implement. And then there's a ton of different backends we need to support. Like we need to run on CPUs, OpenMP processors, GPUs. So there's a ton of code you have to write, and it would take a long time to write that all by hand. So what we did was use this compiler, which accepts basically tensor algebra notation computations you want to run, and then a little bit of metadata about what data structure it's stored in, and kind of what is the recipe you want to use for running that at scale. So to implement something like SPMV, what we did was like, okay, rather than sitting down and start writing out some CUDA, we wrote down a little schedule to Distal saying, here's the strategy I want you to use to implement this computation. And then Distal generated a ton of Legion code. So it generated you that low-level kernel you want, and then also all the partitioning operations you want to use kind of directly to the Legion API. And then once you get your head around using constraints, it's sort of very easy to lift these like Legion partitioning operations into the constraints you want to use. And you can just kind of do that and get out this Legate code that is now like the information described by these low-level partitioning operations and the constraints is roughly the same. But what you get from lifting it to constraints is now the composability with other libraries that may be using the data in a different orientation. And then, yeah, so as a result of this, it still generated nearly half of the C++ and CUDA at the time when I did this, and some small fraction of the Python. And so that was the mainly core of the core tensor algebra component of Legate Sparse. And then the rest of it, well, you can kind of just copy paste a lot of existing code. And because in the work we did in Legate was to really try and make it all composable. So you really do have this situation where once you've hit a certain complexity in the library, like you've implemented all the core matrix operations, then you can just kind of build the rest of the library by composing them with that and other NumPy code. And so all this CuPy, all these big functions inside SciPy, like CG solve, other solves, you just take the code that was written using SciPy and NumPy, change the imports to Numeric and Legate Sparse, and then the rest of it kind of works. And so this is really how we want to be building libraries. You actually do want to compose existing code to get your new code. You don't want to write it all from scratch. And so Legate made that possible. Kind of a lot of these things we've done to get both correct composition and correct, good performance in that composition. So that's kind of the summary. So we have this distributed accelerated replacement for sparse computations. I encourage you to try it if you have some sparse data and you're operating on it in a much lower level. The Legate ecosystem is going to allow you to actually compose this code with the other Legate libraries that have been built. And so you can actually just import just the stuff you need and then maybe build a little bit out all the stuff that we don't have. And if you write a lot of Legion code today, I recommend perhaps trying out the Legate framework and seeing for your next library, maybe it could automate a lot of the stuff that you're doing by hand today. So I have the GitHub repo for this, as well as the conda packages. So even if you just install Legate Sparse, Legate and CuPy Numeric will come with it for free, and just a quick conda install to do it. So yeah, so that's all I wanted to say. Happy to take any questions.